Let us discuss in this video the different number systems. So what are number systems? Number systems are just the different type of numbers that we have already encountered. Okay, and we are going to go through them. And this is going to be basically the way they were discovered. So what is the simplest type of numbers? Those are the natural numbers or whole numbers. These are numbers that are used to count things. So 1, 2, 3, 4, and so on. Okay, these are counting numbers. And they are just used to keep track of things. Okay, we denote them by the letter capital N, and when we write it, we write that double bar. Okay, so with natural numbers, we can keep track of things, but eventually, for example, if we are keeping track of money and we start spending money or using our money, we will want to also subtract. Okay, we will not always add. We will sometimes subtract, and we may run into debt. Okay, so when that happens, we run into integer numbers. Okay, these are the same numbers we already have, the positive natural numbers, the whole numbers. Then we add the 0, and then we add the negatives of all the whole numbers. Okay, these numbers, they don't really make sense in counting, right? Because we don't count negative things, and 0 means nothing, so we don't use them to count. But they make sense, for example, when we are talking about money, as we said, or temperatures. Okay, so they are useful. We denote the set of the integer numbers by a capital Z, and then the diagonal line, we make it double. Okay. Now, when we have integer numbers, so we may want to split something, right? So for example, we may want to divide 4 between 2. Okay, let's say 4 coins between 2 people. This is 2, which is a number in the integers, but then we will run into trouble if we, for example, try to do 5 divided by 2, because this is not a number in the set of the integers. Okay, 5 divided by 2 we know is 2.5, but that's not the whole, that's not a whole number, that's not the negative of a whole number, that's not 0. So it's not in Z. So here we again run into trouble. We cannot always divide. Okay, so when this happens, they say, well, why don't we consider also as numbers? So far we have, if you have noticed, we can represent them on a line, right? We can put the whole numbers on the right, the negatives on the left, and this line represents the numbers. But notice that we are only putting a number in its, they're spaced 1 unit. In between them, there is nothing. Okay, so now we could say, well, let me include also the fractions, okay? For example, the 2.5 we were saying. So these are the rational numbers. These are quotients, okay? And we denote them by a capital Q, also with a double line. In this case, we are going to add all possible quotients of the numbers we already have. So they are of the form A over B where A, B are integers, okay, they can be negative too, and B is not 0. Okay, that's important. And these represent proportions, ratios. As a fun fact, these numbers were actually the ones that the ancient Greeks knew. Okay, they were most interested in proportions. You see, if you see their art, they were always very interested in the different proportions in a sculpture, in their buildings, right? And they actually believed that all the numbers were ratios of, of integer numbers. Now, they eventually discovered that there were numbers that were not rational, and for them that was groundbreaking. Depending on the story you hear, you will hear that they made a party, a holiday, like for weeks, or that they just threw the person that discovered this on a ship on the sea. Okay, I heard both stories. Anyway, so these rational numbers are useful if we want to see proportions, ratios, split things. And now these are, if you have noticed, so far we have seen these sets of numbers, they are infinitely big. Okay, we have infinitely many numbers. But with these rational numbers, it seems there are so many more than we had before. So in fact, there are infinitely many numbers infinitely many rational numbers in the interval 0, 1 alone. Okay. Notice I'm not saying the whole real line, because you could say, yeah, of course, there are infinitely many numbers in the real line. It's unbounded. But in the interval 0, 1 alone, there are infinitely many. This is something that we need to prove. It's not obvious. Okay. So how do we prove there are infinitely many? It's a very simple proof. So you just take two numbers, r equal a over b and s equal c over d. B and d are different from 0, okay? And if you are able to find another number in between, and you can do this every time, then there are infinitely many, okay? So what we are going to do is just find a rational number between r and s, okay? And there are two ways you can do this. In the book, you will see that if you take r plus s over 2 is the middle point and is rational, okay? This is the possibility 1. Possibility number 2, you could say, okay, a plus c divided by b plus d is lies between r and s, okay? Here I'm not saying, I'm not doing, this is not the sum of the two numbers r and s, okay? I'm just saying that if you add together the two numerators and the two denominators, then you get the number that is in between r and s, okay? So let us check this second possibility. We need to check that a plus c over b plus d is in between A over B and C over D. Okay, so let's check the first of these inequalities, then you can check the second. Okay. So to check this inequality, we have to check that AB is smaller than A plus C divided by B plus D. But this is true if and only if we cross multiply A times B plus D is smaller than B times A plus C. And this is AB plus AD smaller than BA plus BC. So these two cancel out. And the inequality we get here is equivalent to the one we started with, that A divided by B, which is R, is smaller than C divided by D, okay, which is true. So because all these are equivalent to each other, they are if and only ifs. If this one is true, the original one is also true. Okay, so now I suggest you try the upper bound. A plus C divided by B plus D less than C over D. Okay, anyway, once we have this property, if we look at the interval 0, 1, then we can, this is 0 divided by 1, and this is 1 divided by 1. So I can add them together, and I get 0 plus 1 divided by 1 plus 1. That's 1/2, correct? Now, 1/2, I can always add them together. 0 plus 1 divided by 1 plus 2, this is 1/3, right? Or I could do the other side. I could do 1 plus 1 divided by 2 plus 1, that is 2/3. So you see, but now I could decide, okay, let me try, well, see what happens here. So this is 1 plus 1 divided by 3 plus 2. This is 2/5. You see what's happening? So in this way, the interval 0, 1 gets populated real fast. And this process will never end, because for whichever two numbers you pick, you can always produce one more in between. So even if you think you are done, just pick two of those and you can produce yet another one and keep going on and on and on. So it looks like the whole interval is basically filled with rational numbers. And now there is another way that we can write them down. We can write them as decimal numbers, decimal expansions. Okay. And here we are going to find three different types of expansion. The ones that are terminating. Well, we have the integers, of course. We have terminating decimal expansions. For example, 0.5. Okay. And we can have periodic expansions. These ones are non-terminating and recurring. Okay, so we can have, for example, 0.123, 123, 123, and so on. Okay. So in Calculus 2, we learn how to write this as a fraction. Okay. But then here we run into a problem. What happens with a number that is, for example, let's say 0.1, and then I write a number 2, and then 2 ones. Then a number 3, 3 ones. A number 4, 4 ones. What comes next? Number 5, and then 5 ones, and so on. The rule that describes this number is clear, right? But is this number terminating? No, this is non-terminating. But is it recurring? No. So this number is not among the decimal expansions we have already considered. So this is a different type of number. Okay. This is what we call an irrational number. Okay. This cannot be written as a fraction. Okay. Other examples of irrational numbers. We have the famous pi, the number e. We have the golden ratio. Pi. There are so many. Okay. So what happens when we put together the rational and the irrational numbers? Then we get, you see, this was the third type of numbers. We get the real numbers. Okay, this we denote with an R with a double line. And these are the rational and the irrational. Okay. So here basically completes, when you look at the real line, any dot that you pick is a real number. Okay. Before, if you look at the rational numbers only, the line will look full to you, but it's actually not full. We will go over this later in the semester. Okay. And by the way, there are two types of irrational numbers. The algebraic, they are given by a formula with a polynomial, and then there are the transcendental. Okay, so examples of algebraic are the square root of 2 and the golden ratio. Transcendental, we have pi and we have e. Okay, and finally, because we will cover this later in the semester, we also have complex numbers. Okay, and these are a C with a double, with a line. Okay, these ones are the ones that come when we try to solve something like x squared plus 1 equals 0. Okay, this is not possible because x squared equals -1. Well, we have a positive number on the left and negative on the right, so it's not possible in principle. But then if you decide, okay, well, let me define the number I equals the square root of -1, move on. Okay, and it's very useful. So the reason why we study this is because it's useful. And these are numbers of the form a plus ib, or we can just write them as a pair, ab. And they are not in a line, they are on a plane. Okay, so it's A plus IB or AD. So this is A and this is B. And these are all the number systems.